Hello, everybody.
Hello.
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 Hello. I'm trying to check my speakers. Can someone say anything, please?
I can hear you, Victoria.
Okay, thank you. I was like dead silence. I was afraid to do that.
Excuse me. Sorry. Ugh. Is there anybody who wasn't here? Actually, no, I'll wait a minute. I'll wait a minute. One minute, and I'll get started here. All right, it's 12:30. We'll get started. I know of one person who wasn't here on Monday who's contacted me already. Is there anybody else who wasn't here on Monday? Could you alert me now, please? Okay. All right. I need to send an email to that person, which I'll do now. Just give me a second here, folks. All right. We'll get started now. I need to, first of all, share my screen here, which I'll get to in a second. Here we go. Okay, there we go. All right, so there's a lot of stuff I have to have on the screen here. It's quite interesting. I have to have the chat box up here just in case somebody doesn't have a microphone. That takes up a little bit of real estate. I've also got to have my drawing pad here as well, and the PowerPoint. So I can't have that as a full screen. Whoops. That's probably why it's not a bad idea for you to have those printable notes as well. All right, there we go. But that's how I want it set up, for me at least. Okay. So is James here? James, are you here? You were earlier. I know you were. I saw you pop in.
I'm right here.
Oh, thanks. Thanks.
Under Jim. Yes, sir.
Yes. I sent you a handwriting exemplar. Follow the instructions in the syllabus and then put that in the first day folder, please.
Okay, great. Thanks so much.
Thanks. All right. Let's get started. So we're dealing here with the very basics here. We know about the rows of electrons and how they're emulated by the periodic table, 2 in the first row, 8 in the second row, 8 in the third row. But after that, you can see it goes 2. Don't worry about this here. It's got hydrogen in 2 places, but that's okay. You got 2 here, then you got 8, then you got 8. That's how we know how many are in each row. And we know we want everything to have 8 electrons. So at the very core of this, and the very core of organic chemistry, we're going to have carbon needing 4 bonds because it's in group 4. It needs 4 electrons. Nitrogen needs 3 because it's in group 5. Oxygen needs 2 because it's in group 6. And fluorine needs 1 because it's in group 7. Everything wants 8 electrons. So that's going to determine how many bonds each of these things has. So we know that carbon, 4 bonds, nitrogen, 3 bonds, oxygen, 2 bonds, fluorine, 1 bond. And that's going to form the very foundation of every single structure that we draw in organic chemistry. So, I'm never very happy when I see people put the wrong bonds on these very basic elements. So that's something to watch out for. Remember, the whole aim, when you certainly when you're doing a test, is you want me to think that you know what you're doing. And when I see people put 3 bonds on a carbon or 4 bonds on a nitrogen, and it's a neutral compound, those kinds of things, then I begin to think that maybe you don't know what you're doing. You don't want me thinking that. Okay, so it's a very basic thing that I want everybody to sort of form that foundation of there. The other thing that's important is electronegativities. You'll notice I'm going through this fairly fast because most of it is review, and I'm really just trying to give you a very basic foundation at the present time before we get on to some real problem solving. I'm hoping that you've watched the videos that I had suggested you watch in the syllabus as well. Okay, so electronegativities. We know that the fluorine is going to be the most electronegative element, and these numbers are Pauling numbers, and you can see everything's based on fluorine, and that it goes pretty much from fluorine all the way over here to this side of the periodic table, which is the metal side, and you'll see it goes down to 0.9, 0.8, 0.7 possibly. Okay, bond types. Now these are going to be important to us, and this is where I'm going to start going into a little bit more detail. We've got three bonds that we're going to talk about. We're going to talk about ionic, we're going to talk about polar covalent, and we're going to talk about non-polar covalent. So a bond, what is a bond? A bond is going to be two electrons in between two elements that join those two elements together with a bond. In the case of an ionic bond, it's called ionic because it's made up of charged particles. Charged particles are called ions. So sodium plus is an ion, F minus is an ion. These numbers here, these are those Pauling electronegativity numbers I showed you earlier. Delta here, that's the difference between the two. Turns out 3.1 is a pretty big difference. And the bigger the difference, the chances are it's going to be an ionic bond. I'm going to show you an easier way of doing this rather than using the Pauling electronegativity scale in a second. Just know that a large difference in electronegativity is going to lead to this kind of ionic bond. But what in essence is it? Well, I told you that a bond is two electrons between two elements, and you can see them there on the screen. But the nature of the ionic bond is such that the two electrons are actually really on one of the elements. As it turns out, the more electronegative element. I mean, the electrons are so close to one element, you could actually say that one element has taken an electron from the other. And that's what's caused these charges here. So as you can see, I've drawn these two electrons very close to the Y, which is emulating the F here in this example. Does anybody have any questions so far? You'll know
Can you hear me?
Yes, I can hear you.
So the bigger the change in the Pauling scale, the number there, would that also mean kind of the stronger the electrostatic bond between the two?
Yes, that's right. So that's a very strong ionic bond is what you're going to see there with a very large. I know you might be wondering, well, what's large, what's small? Well, generally anything bigger than 2 I consider large for a difference. And I'll show you the implications of that in a second. Actually, it says 1.5 here, but 2, 1.5. You know, it all varies. You'll see different things in different textbooks.
Can I ask a question?
Yes, absolutely.
I see here, I'm not really sure how to read what I'm looking at to begin with. It says X here, and then it has a Y. This is just.
These are
like,
just two elements. Yeah,
okay.
they're just example elements.
Okay, here it says 9, and here it says 4, but
0.9,
then
0.9.
0.9, and oh, okay, now I get it. All right, I didn't see the point. Thank you.
You didn't get the point, Julie.
I'm thinking 9 minus 4 is not 3.1. Okay, thank you.
All right, let's take a look at the other couple of examples here. This one is polar covalent. Take a look at the difference between the two. Do you see where the electrons are? They're not that close to the Y, but they're still closer to the Y than they are to the X, but they're in the middle. Now look at the difference between the two. We've got 2.5 and we've got 3. The difference is 0.5. So what this means is that we end up with what's called a polar covalent bond. So these electrons are truly shared. That's what covalent means. They're shared. In this case, there ain't no sharing going on. Na has given, F has taken. That ain't sharing. This is sharing because the electrons are in between the two elements. That's the distinction I want you to see. And the reasoning for that has to do with the difference between the electronegativities. You know, these elements are having a pull on the electrons. Look up here. The fluorine, because it's so electronegative, and the sodium, because it's so not electronegative, leads to a situation where the electrons are pulled toward the electronegative element. Whereas over here, they have sort of more of an even pull, but still the chlorine is more than the carbon. So it puts the electrons kind of in between the carbon and chlorine, but closer to the chlorine than the carbon. I hope that all makes sense. Does anybody have any questions so far?
Can I ask a question?
Yeah, go through.
About the charge itself on a carbon or chlorine, the 3.0 and 2.5, are they from a chart?
Yeah, they're from this chart that I showed you back here. This Pauling electronegativity
And where
scale.
is that chart?
Oh, where is it? Well, it's here. It's in the PowerPoint. But it's also on any standard periodic table.
Okay.
You'll see it. It's usually an item on at least a Sergeant Welch one, but you can look it up on Google as well.
Okay.
You'll see them there, but it's all based on this scale. F is 4 and everything else is less than that.
Okay.
All
Thank
right.
you.
So what you'll notice here is that I have gone ahead and I've put these little thingies on here, delta minus and delta plus. So what do those mean? Well, those are called partial charges. And of course, what we're going to say is that the delta minus goes on the more electronegative of the two. It just means that the electron density is sort of closer to the chlorine than it is to the carbon. I'll draw a little diagram of that over here. Let's see if I have. There we go. So if you've got carbon and you've got chlorine, the electron density is going to kind of look like this. And the electron cloud is kind of going to be drawn more towards the chlorine than the carbon is. So that's why we put a delta minus there and a delta plus here. Now those aren't full charges, folks. They're not full. They're just they're partial. That's why the little delta is there. These deltas are going to be important later. Don't ignore them. I love my deltas. I do. You'll learn this. You'll see that I do. And I won't tolerate people disrespecting my deltas. All right, I'll continue on. So there's the difference. You can see the difference between the two. I want to make the distinction. Look where the electrons are here in the ionic. They're very close to the F and the Y here, the more electronegative. And here they're sort of in between, but closer to the more electronegative one than they are to the less electronegative one. And then we put these partial charges on here. Does anybody have any questions so far?
That's just a representative of the amount of time it spends around the particular atom, right?
I wouldn't say time. I'd say it's just where the electrons are pulled towards.
Sure. Let me reword. Like it will circle the chlorine more than it will circle the carbon.
We can say that.
Okay.
Yeah. But generally, it's more like a cloud that kind of gets pulled in one direction.
Okay.
Over the other. Think of it more like that, rather than just because the electrons themselves are. Well, it's hard to explain what they're doing, but they're not really moving per se. They're in certain spaces. We'll talk more about that when we get to orbitals and things.
Oh, we have a question in the chat.
Oh, I'm sorry. Yes, I see it. Oh, do we need to memorize charges for the elements? I will show you how to do that, Nora. It's not really a memorization. We can look at the periodic table and figure out the charges easy. Okay, so don't get too worried about having to memorize a whole bunch of stuff. Thanks, Nora.
Thank you.
Yeah, I'll yeah. Alert me if I miss something in the chat. I'm often have my attention somewhere else. All right. The last one here, non-polar covalent. Look at that puppy. Look where the electrons are. Smack dab in the middle of the two. Why is that? Because the two carbons have exactly the same electronegativity. They have exactly the same pull on those electrons. So the electrons are smack dab in the middle of the two carbons. There is no difference in the electronegativity, of course. And most importantly, no delta plus and delta minus because the electrons are in the middle. They are not closer to one than the other.
So for the greater the delta of the electronegativity, does that mean the bond is going to be stronger as well?
Stronger, yeah, I'd say that that's probably true. I'd say the strongest bond types do tend to be the ionic bonds, and I know this because ionic compounds tend to melt at very high temperatures. I mean, it takes probably thousands of degrees to melt something that's ionic, whereas these covalent compounds tend to melt a lot lower, you know, in the 100, 200 degree range. But
What
yeah,
about pure metals like tungsten?
well, that's a metallic bond. That's a different kettle of fish. And I'm not really going to be focusing on those bonds because this is organic chemistry. All right, is that okay? I don't mean to be sarcastic about that. I just.
Oh yeah, that's fine.
All right. Does anybody have any other questions about the bonding so far? Let me just summarize this a little bit. So for the ionic bonds, we're looking at an electronegativity greater than 1.5. For polar covalent, about 1.5 to 0.5 for the difference in electronegativity. We're talking about difference here. And for non-polar covalent, less than 0.5 difference, but effectively 0, really. Now, you might be saying, oh gosh, I don't want to have to memorize those numbers. Do you want to have to memorize those numbers? No, you don't want to memorize those numbers. All right, let's take a look. Let's see how we can avoid that. I'll just take this periodic table here. So what we notice is that if you remember the Pauling scale, it started out here as 4, and then it's over here, it was like 0.9. So, you know, there's a progression as we go across the periodic table. But here's my point. Here's my point. If you've got a large difference in distance between two elements, like you've got something over here and something over here, we're talking ionic bonds. Right? Ionic bonds are generally between metals and non-metals. And if you remember where the non-metals are, they're on this side of this steppy business, right? If you remember. So anything between a metal and a non-metal is going to be what we call ionic, because the difference in electronegativity is going to be great. Now, let's say you've got two non-metals, but they're different from each other. So let's say N and F. I know that's going to be polar covalent because it's close. Look how close they are. And then if you've got the same element, that's going to be covalent.
Neutrons would not have an effect on electronegativity, correct?
Not really, no. No, really, well, what it's about is where the things are in the row. So F is at the end of the row here, and it wants electrons, so that makes it more electronegative. But it really has nothing to do with neutrons, I don't think. So what we can come up with here is a hierarchy of polarity. And this is going to make sense to you, I hope. It's going to be ionic is greater than polar covalent is greater than non-polar covalent. Now, non-polar covalent, of course, is two elements that are the same as each other. There's no difference in electronegativity. So that's the upshot I want you to get. And you can get an idea about polarity by looking at the difference in distance between the two things on the periodic table. The bigger the distance, the bigger the difference in electronegativity, the bigger the polarity.
So what if they're right next to each other?
Well, you know, I would still say polar covalent. I would.
Okay.
They won't have huge differences in electronegativity, but it'll still be big enough, I think, to be polar covalent, to say polar covalent.
So with the ionic bond notation, we used X positive and negative, but then in the polar covalent, we use partial charges.
That's correct, yeah.
What is the reason for that? Why are we using partial charges for one but not the other?
Okay, that's a good question. It's a good question. I like it. Let's have a look. So in the case of the ionic, the electrons one has actually been given to another. So it actually gets a negative charge, and the other one, since it's lost an electron, gets a positive charge. But that's because it's give and take. The Y has actually taken from the X and, run away. But in the case of the other one, look what happens. See, they're in between, but they're shared. It's just that one has it more than the other.
Oh, so because they're sharing, one's going to become a little bit more negative of a charge. Okay, I gotcha. Thank you.
Yeah, that's what I.
And then the one with the non-polar, it's because they're the same element and they're equally sharing.
Dead right. That's exactly right. So you see, I've got this on here: lowest polarity. Sorry. Oh, I didn't have it here, but this is sort of medium polarity. This one's the highest polarity. So this one's sort of in between. This one here is in between. All right. Any questions about that? Okay. Now I will apply this to the test questions in a bit. All right, but I want to get through the other stuff first, and then we'll go take a look at the test and see how this relates to that. But does anybody have any questions about what I've got here with the polarity? This is the upshot of it, and how you can relate that to distance apart on the periodic table. All right. All right, let's talk about a little bit about structure expression. We're going to be mostly focusing on line structures, and in the lab, that'll be the first thing we'll do. We'll do some structures and things, but I'm going to make you do line structures on those. But let's look at some different kinds of structures that we'll see in organic chemistry. First of all, you've got the empirical formula, which is really just a ratio of atoms. It doesn't actually show you what true formula is, just tells you that there's 3 hydrogens here for 1 mole of carbon, for example. The molecular formula tells you exactly how many of each element you have in the molecule. The condensed starts to give you some idea about how those might be arranged, and then the structural formula tells you exactly how they're arranged, what's bonded to what. So you see we'll have some notation here. Like when you're using parentheses, this isn't too bad. You've got CH3, parentheses 2, it means there's 2 CH3 groups, and you'd express it like this as a structural formula. Double bonds as well, you can see that. That's just sharing of 4 electrons instead of 2. These are just examples of structural formulas you might see. Now what's important here is your line structures. This is what I want you to be able to focus on here. So the line structure, what we do is, because, here's the thing. Do you really want to be writing out every single carbon and hydrogen? No. I'm going to move myself over here a little bit. Here we go. Do you really want to be writing out every single? No, you don't want to be doing that. So what you want to do is you want to figure out a way that you can shorten it down a bit. And that's what a line structure is. It allows you to assume every single point, including these end ones here, are C's. And then there's enough hydrogens on that C to make up 4 bonds. Why is that? Carbon wants 4 bonds every single time. So
has 4 electrons.
Yeah, it has 4 electrons, so it wants 4 bonds to get to its octet. That's how you got to think about it. To get 8 electrons. All right, so what we're going to do is I'm going to show you how this relates to this, and you can see that we've got the C's here. You've got the C in the middle, and then you've got the 3 C's attached to that, and those are CH3s. Now, what you'll count here, look at the number of bonds we've got. See how you got 1 bond from this middle carbon out to the end? That tells you 1 bond is accounted for, and that's how we know there must be 3 hydrogens on that carbon. If you look at this carbon here in the middle that I'm pointing to with my cursor, you've got 2 bonds. That means there must be 2 hydrogens on it. Now, here you've got, let's see. Yeah, and of course you've got this C here, if it's already got 4 bonds on it. So that's going to have no hydrogens on it. You can see that. And this one here has got 3 bonds, so it needs 1 hydrogen. Does anybody have any questions about that?
Yeah,
Yes.
I'm not even sure what the question. So you're putting C's on every single point,
Mm-hmm.
and the bonds are the lines, right?
Yes.
So how does like you're writing CH2, but wouldn't there be bonds between the C and the other H2s?
Yeah, I've shortened those out. I haven't shown those. I've just put CH2 there to show that
So
there's
what
2 hydrogens.
decides whether you how do you make that decision?
Oh, it doesn't really matter, Julie. It's not the point.
Okay.
Because I could have drawn the 2 hydrogens off there, or done what I've done here. That it's a difference between this structural formula and condensed formula. It's really the same thing. But do you see the difference? CH3 with three hydrogens drawn onto the carbon, and that's just CH3.
I think what he's doing is he's just making all the hydrogens implicit hydrogens, not drawing any of them.
Yeah, not drawing any of them in with the bonds. That's all.
Okay. Thank you.
All right.
I had a question.
Yeah.
Now, is it always going to be assumed that, at the ends of these lines, the very, left and right of that first picture we see with just the sticks,
Yep.
that the carbon's always going to have hydrogen or some other element filling up its kind of bond needs?
Only hydrogen. Only hydrogens. If we're talking about line structures, you assume they're hydrogens.
Okay.
Because I'm going to show you what happens if it's not a hydrogen there, okay? I'll show you that in a second. And that is if we've got what's called a heteroatom. Heteroatom is something other than hydrogen or carbon. So if you've got an OH here, then you can see that what happens is we've got a bond from a C out to an O, and that is expressed as a line from the C out to the O. And there's no carbon here at the end of that line. At the end of this line is the O. So I want that to be clear as well. All right, do you see the connection here?
So what's the molecular formula for this structure?
The molecular formula, let's see, 1, 2, 3, 4, 5, 6. So C6. And hydrogens, well, let's see, we can count them. 3, 5, 7, 9, 11, 14. C6H14O would be the molecular formula.
So just one O.
Just one O, that's right. And you can see it there. Now, traditionally, I didn't say this on the PowerPoint. Traditionally, we usually put the H on the heteroatom. We don't put it on the carbon, but we'll put it on the heteroatom.
So why would you have the H with the O? Like, why couldn't you do CH3 attached to another CH3 attached to an oxygen? You have to have the hydrogen on the outliers?
Well, I mean, if this is the compound and it has an H on the O, then we still need to have the H here. What I'm saying is you wouldn't just leave the H off and just leave it as a blank O. That's all I'm saying. Does that
Okay.
answer your question?
Yes.
Okay. All right. And any other questions about this?
Yeah, so you only assume that there's an H on the carbons. If it's any other element, you have to attach a hydrogen to it.
That's right.
Thank you.
Now, as many hydrogens as it needs. Okay. What I'm going to do is I'm going to put an example here on the screen. And what I'm going to get you to do, you're going to do some work here now. And I'm going to get you to draw the line structure. Actually, no, I'm not. I'm going to draw a line structure. You're going to figure out how many hydrogens there are on each carbon atom. All right, so here we go. Whoops. Sorry. Let's try that again. There we go.
Do you just want us to keep it in our head or tell you when we know?
Oh, no, you can No, what I'll do is I'll do it here, and then I'll put the answer here, and you can compare your answer to this. Okay. Okay. So your mission here, just once again, your mission. Everywhere you think there's a C, draw a C. Okay. And if you draw a C, put how many hydrogens there are off that C, if there are any. Is everybody clear about what I'm asking you to do? If anybody's not, say so now. Okay. So go ahead and write that down. Write down that structure. And then put a C in everywhere you think there's a C. And then how many hydrogens do you think there are on each of those Cs? Yeah, rather than put it on there, I'll redraw it here. A little bit changed. Okay, same thing. All right. But I'll put the C's on the bigger one here. Okay, so here's how it goes. There's a C here, there's a C here, there's a C here, 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 and C here, and a C here. All right, is everybody okay with where the C's are? Okay.
Yes.
All right, let's put the hydrogens on. We've got 3 here. We got 3 here. We've got 3 here. We've got 2 here. We've got 3 here. We've got 1 here. We've got 1 here. We've got 1 here. We've got 2 here. We've got 3 over here. And that's it. Oh, and, you know, up here, you can see there's none on that one. So you can see how I got the number of hydrogens, right? You count up the bonds and you subtract that from 4. And that tells you how many hydrogens you're going to have.
The single H's that connect to the nitrogen and oxygen
Yes.
on the right side.
No, well, actually, just to the nitrogen, right?
Okay, the C is connected to the nitrogen.
Mm-hmm.
Oh, you know what? I see it now. 1, 2, 3.
Yeah,
Okay.
now remember, yeah, that's the other thing. See, remember what I said earlier. We know that carbon has 4 bonds. We know nitrogen has 3. But we didn't have to worry too much about that because I already had the hydrogen on the nitrogen. That was all right. And oxygen only has 2 bonds.
Okay. Mm-hmm.
All right. Anybody got any questions about line structures here?
So you don't include double bonds in this, would you?
Well, no, because I didn't have any to begin with.
Yeah, but if you did have
Or-
something that had a double bond in it, would you include it in the line structure?
You sure would. So let's let me see if I can do that here.
It's just a second line next to that first line, right?
Yeah, I'll draw an example. I'll draw an example. It's a good question. It's a good question. So let's say we had something like that. Oh, sorry, did it again. Okay. Let's say we had something like this. I'm not going to make anything too complicated. All right, so let's say you had that. So what would happen is you'd still do the same thing. You put C, 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 and C. And then you would have 3 hydrogens, 3 hydrogens. And this would only have 1, and this would only have 1. And this would have 2, and this one would have 2. So yes, you'd leave the double bond in there. But it, you know, it accounts for the number of bonds it says it does.
Okay, thank you.
All right. Any other questions?
Quick question.
Yes,
So the lines count as one bond, right?
they
Not
do.
two?
That's, well, this one here, but this one counts as 2 because there's 2 lines.
Right, because there's 2 of them.
Yeah.
Okay, great. Thank you.
All right. Any other questions? All right. So this is something you're going to get good at as you go. We'll be drawing line structures. But they're not too bad, really. You'll survive. Hundreds of thousands of students before you have done this, and you'll succeed as well. All right. Okay. Let me see what we're covering today. That might help. I want to see how far I'm going in the syllabus here. And I'm not going to go any further than what I'm going here. All right, let's have a look. I want to get to intermolecular forces. Yes. So let's stop. That's where we're gonna stop. Once we get that done, we're just doing the intermolecular forces. We're not going any further than that. Okay. Intermolecular forces. So I'll get you to watch that video. It's part of the PowerPoint. You can start the PowerPoint up. You can watch that video. It shows you the difference between. Well, I suppose I'll show it. I'll have to give me a second. Give me a second. It's kind of a cool video. I can't not show it. All right, slideshow from beginning. Oh, I didn't want to do it from beginning. I want to do it from the current page. Yeah. Let's see if this will open up. I hope it will. Why is it not opening? There we go. Yeah, it will. There we go. Yeah, I kind of like this. So this is on the PowerPoint. You have access to it as well. So let's look at phase changes. There we go. So that is a solid, what we're looking at there. Solid neon, actually. And you can see in the solid that everything's pretty well ordered and that there's still some movement though, right? There's still some movement because we're not at 0 Kelvin. But let's look what happens when we heat him up. Oh, look at that fire. Oops, sorry. There we go. Now this here is more like a liquid. As you can see, there's a lot less ordering. But you'll notice that, well, most of it, except for this one here, they're all touching each other, right? Or at least there's some contact between them, for the most part. That's liquid. That's liquid. Heat him up a bit more. Let's see what happens. Going crazy here. Going crazy. There you go. Look at that. So that's gas. Now, what's the difference between liquid and gas? The difference is that in a liquid, the molecules are all touching each other. There's some contact between them. But look at the gas. No contact, right? I mean, sure, they bounce off each other and whatnot, but that's a clear difference between the gas phase and the liquid phase. Anybody got any questions? Any questions? All right, good. All right, I like that. I like that too. I like that a lot. All right, let's talk about what keeps these things as liquids. You know, I mean, the thing is, if things are keeping these molecules together, I mean, if these molecules are touching each other, there must be something keeping them together. And what's keeping them together are these, what we call intermolecular forces. Remember that these are molecules. So molecules are being kept together by something. So in the case of the van der Waal, that's the first force we're going to look at. We're going to look at three forces here. The first one is going to be van der Waals, also called London dispersion forces. We're also going to talk about dipole-dipole forces, and we're going to talk about hydrogen bonding. That's the third force. Okay. Van der Waals forces. These are the weakest of the three intermolecular forces we're going to talk about. These are the forces that we see in hydrocarbons. What's a hydrocarbon? Well, not surprisingly, a hydrocarbon is something that has bonds between hydrogen and carbon. All right.
You just blew my mind, Musgrave.
I know, I blew my own mind just now. It's amazing. Okay. So what are we looking at with these London dispersion forces? Well, I want you to imagine that with all these CH bonds, we've got what amounts to an electron cloud. That electron cloud can actually move. It can move a little bit. But it's only temporary movement that results in these partial charges here. But it's temporary. I'm going to show you an animation of that. Whoa, that's unfortunate. I'm going to have to fix that link, aren't I? All right. Let's go back to oh, you know what? I know what I'm going to do. I know exactly what I'm going to do. Now, the thing was, I made these videos for another purpose, you know, these mini lecture videos. And what it does, it's kind of like a time machine in its own way, because any of these things that the links change, I've still got a record of it because I did a video of them. There's all sorts of illegal around that, I'm sure. Let me see if I can find it. Oh, intermolecular forces. Yeah, there we go. I'll shut that person up. Okay, let's see. Oops. Sorry. There we go. Okay. So this here, you can see the picture of it. That's Van der Waals right there. That little animation that I'm showing you there, that's Van der Waals. You can see that the electron cloud is moving from side to side, but it's only temporary. It's only temporary, folks. I'll stop that for a second. I'll pause it. And then I'll go back to where we were. Here we are. So that's the nature of it.
Get into the physics department real quick here.
Mm-hmm. I'm sorry, what was that? Did you have a question?
Yeah, I feel like this topic can get into the physics department real quick.
It can, but I'm trying not to. I want to try and keep it as simple as I can, but no simpler.
I'm not sure I understand your circles and that weird shape, the light bulb shape things. When I'm looking.
Okay. So I want you to imagine this oval here is, see these CH bonds? It's like the electrons in those, right? And so it's creating this electron cloud. Because remember, between each of those C's and H's, there's 2 electrons, Julie. I want you to imagine that in an unchanged CH system, it's just going to look like that oval. But what happens is, and that's why I've got these arrows here, you have electrons can move from between one side and the other. It's still going to be the same volume, if you will, but you know, it's like if you've got a balloon. Think of a balloon, Julie. Think of a balloon. And you know how you can squeeze the balloon at one end, and what happens? It pops to the other end, right? Think of it like that. Think of it like a balloon. Is that all right?
Yeah.
Sure?
No. Okay, so I'm looking at a balloon, and
you can, the thing is, if you pinch the balloon at one end, it gets bigger at the other end, right? That's kind of what's happening here. Think of it that way.
With forces.
Well, with the electrons are moving.
Okay.
Now, that's a bit exaggerated what I've got there, but I'm trying to put across a point here.
Is there something that causes the movement, like the heat in the last one, or is this just the nature of electrons? They don't stay.
That's exactly right. It's just the nature
Okay.
of electrons. It's all quantum mechanics, Rebecca. And as somebody had said earlier, it moves into physics pretty quick.
Okay.
But we don't want to go down that road.
No, we don't.
So what's the difference between the three rows we're looking at?
Okay, well, right there. So down here, you see how when it shifts, what that means is the bigger side, the fat side here is delta minus, and the skinny side here is delta plus. There's more electron density over here, right?
Right.
So what that means is that they can line up because you've got this attraction between the delta plus end and the delta minus end. That's the attraction. And you see that attraction there is what keeps the molecules close together, Julie.
Okay, so the top one and the middle one are only one molecule and the bottom one are three. Is that what you're saying?
That's what I'm saying.
Okay.
Yeah, is that all right?
Yes.
Okay. So the next one is called Dipole Dipole. Now remember, this one was all C's and H's. C's and H's, I'll say it again. C's and H's, right?
H's.
This one is CX, where X is any nonmetal. Nitrogen, oxygen, sulfur, halogen. And this results in a permanent dipole. This puppy here, the Van der Waal, temporary, which makes it weak. This one here, permanent, which makes it a whole lot stronger. How much stronger? 10 times. 10 times. So what happens is, let's say we've got a CX where we've got CF here. Now remember that the delta minus always goes on the more electronegative of the two elements. And we know F is more electronegative than C, so the delta minus goes on the F, the delta plus goes on the C. And then you can see that same attraction between them. But the delta minus and delta pluses are much bigger here than they were in the previous one, because this was only temporary and this one is permanent. Does anybody have any questions about the distinction I'm trying to make between these two?
Is X only going to be equal, or for our purposes, is X only going to be equal to these elements, the halogens, NO and S?
No, I'd say about those are just examples. X could really
On
be
this one.
any nonmetal. Any nonmetal. But for most of the time, I'd say 99% of the time, it'll be one of those four, or halogens are the chlorine, fluorine, bromine, and iodine. So any one of those 7 generally. But the same thing would apply to P as well. Phosphorus.
So the dipole is just the movement between the electronegative and the electropositive sides.
Is it the movement? No, it's not so much movement. It's more like attraction. The electrons are more attracted to the F than they are to the C. So it's not really so much movement as it is attraction.
Oh, okay.
Let me show you the animation for that. See if I can find it. There he is. Okay. There we are. Yeah, so you can see this is a dipole-dipole interaction. You can see those are permanent dipoles, and you can see what's attracting them there. They're just attracted to the delta plus, delta minus, and it's 10 times stronger attraction than we had in that previous one, which was all temporary dipoles. If I can find it. There we go. See that? Temporary, temporary, temporary. Look at that. Temporary.
And does that have to do with them being the same molecules? like not having the non-metal and metal?
Right, because the CH bonds are not very polar.
Yeah. Gotcha.
Whereas,
So if I might be thinking of this wrong, but in the van der Waals forces, if you apply a continuous force to whatever molecule is undergoing these forces, at some point it's going to be the force being applied in that transitionary period, and that point there's nothing holding them together, right?
well, yeah, but there's always going to be some molecules in the system that are moving, you know, have their charge moving, but it's only temporary. But they're not all doing it at the same time in reality. But it's enough to tie them together at least weekly. W-E-A-K-L-Y, I mean, weekly. At least weekly holding them together. Is that all right?
Yep.
Okay. The last one is called hydrogen bonding, which is a horrible name for an intermolecular force. Awful. I just wish they'd come up with something different. That is a horrible name. It looks very molecular or intramolecular to me, but it's called hydrogen bonding. It's a very special kind of dipole-dipole force that results between specifically OH, NH, and FH bonds. That is our friend, the hydrogen bond. And the reason for this, and I'm not going to go into it too deeply, you can see more about it in the video, is that hydrogen is very small relative to O, N, or F, and that results in a much stronger delta plus, delta minus type situation here. So these are going to be very strong intermolecular bonds that we're talking about between a delta plus and a delta minus. 10 times stronger than your garden variety dipole-dipole bond. All right, does anybody have any questions about that?
So test-wise, we're probably just going to need to know the concepts and be able to recognize which ones are which.
Yep, that's dead right. Dead right.
Okay.
Now, I will show you how to do that in a minute, okay?
Perfect.
You mentioned bigger and smaller charges. I know I've seen these written where they'll have a delta that's actually larger in size than the other one. Is that what you meant, or you're just saying positive and negative right now?
No, I am saying larger delta, bigger deltas.
Okay, because I think I mean, this is pretty tiny for me, but they all look the same size right now.
I know they do, but I'm just,
okay.
but I'm trying to make a point, just to make a point about the size of them.
Okay.
More orally than I am with the deltas.
Okay. All right.
But you can do that. You're right. Okay. What else will change intermolecular forces? Well, we've got straight chain versus long chain. That's going to be interesting. Yeah, you got to think about long chain as being greater surface area than short chain. So if you've got long chains here, they're going to have more opportunities for interaction than short chains. So the intermolecular forces between long chains are bigger than short chains. Anybody ever got any questions about that? I'll apply this. You'll see it's real easy to see this when we've got our problems, okay? Don't panic. I'm just giving you the concepts here. The other thing is that straight chain is always going to be stronger than branch chain. Now, the difference between those is that straight chain is just C's all in a row, and then branched is when you've got C's in a row, but you've got C's coming off that row. Now, the way I want you to think about this is that the straight chain is kind of like cigars in a box, and there's a lot of surface contact between the cigars. Whereas branch chain is kind of like spheres in a box, and you're not going to have as much surface contact between the spheres. Don't panic. I'll show you what these look like as structures soon, okay? Don't panic, okay? I just want you to get the concepts here, okay? I'll put it all in a nice little bow in a minute. Okay. What else is important here? There's a relationship then between intermolecular forces and boiling point. So boiling point, what is that? Boiling point is the temperature required to turn the liquid into a gas. Liquid phase has the molecules touching. Gas phase has the molecules not touching. So boiling point is the temperature required to have the molecules not touching each other anymore. I'll stop there for a second. Is everybody okay with that? All right, it's the intermolecular forces that keep the molecules touching. The stronger the intermolecular force, the stronger the higher the boiling point. Okay, let me see if I don't know if this works. We'll see if it works or not. Oh yeah, cool. All right. I just want to show you a couple of examples here. Now these are chains of different lengths. Do you remember I was talking about short chains and long chains? As we go, this is short, this goes down here to long, right? So you've got how many in this one? 5, 6, 7, 8, 9, 10, all the way down here. Just stop here at decane. Look at the boiling point. 36, 69, 98. Gets bigger. Why is it getting bigger? The chains are getting longer. More surface contact between these puppies, all the way down. Now, tetramethylbutane, let's see, I'm going to draw a picture of that one differently. I can, here we are. All right, tetramethylbutane, that looks like this. That is branched, right? It's branched because it's got those CH3 groups coming off. And look how many carbons there are. There's 8 total. Do you all see that? 8. So look at that, compare it to octane, which also has 8. So this one is 126. That one is straight chain. That's 8 carbons in a row. One, 2, 3, 4, 5, 6, 7, 8. Okay. That's 8 carbons in a row. That one has a lot of surface contact between the molecules. 126 degrees Celsius is the boiling point. This one here has the same number of carbons, but it's only 106 degrees. Why? Less surface contact. This is more like cigars in a box, or it would be if I drew it out straight. And this one is like spheres in a box. So the forces are less. I'll stop here for a second. Anybody got any questions?
Yeah.
Yep.
Is there a way to know by looking at the formula how it's laid out?
Yeah, you can see it here. See how you got C? It's got 3 CH3s connected to it. And this C has 3 CH3s connected to it, and I've just drawn it out like that. If you look at the octane here, you've got CH3, then you've got 6 CH2s all joined together, and then the CH3 at the end.
But how? I still don't get how you know that these were in a row and these weren't, because of this.
No, just from the way it's laid out, CH3, then 6 CH2s. The only way that you can lay that out is all in a row. Whereas this one here has C with 3 CH3s on it. We can talk about this later, Julie.
Okay.
So with the IMFs, is that between molecules in
It is.
one atom, or atoms in one molecule, or is it between different molecules of the same compound?
Different molecules of the same compound.
Gotcha. Thank you.
Yeah. So, a whole bunch of these together,
So it's the attraction force between like molecules.
Mm-hmm.
I gotcha. Okay.
Mm-hmm. Yes. I love this here. This is really cool. All right, so let me see. I'm going to enlarge this a little bit. So what we've got here, just so you can see what the progression is here. These are all compounds of hydrogen and certain elements. These are group 4, these are group 5, these are group 6. Sorry, apologize. There's group 4, that's group 5, that's group 7, that's group 6. Yeah. So what I'm talking about there is, you know, like on the periodic table, which I don't know if I have one of here, but we'll see. I'll go back to it. Here we go. So we're talking about here, group 4. This is not helping. This is not being very helpful. I'm going to get out of that. There we go. I lost my mouse. My mouse does not seem to want to grab onto this at all. It's not behaving. All right, but we've got group 4, which has carbon, silicon, germanium, and tin. Group 5, which is nitrogen, phosphorus, arsenic, and antimony. Group 6, which is oxygen, sulfur, selenium, and tellurium. And then group 7 is fluorine, chlorine, bromine, and iodine. And what I'm showing you here are hydrogen compounds of those. Now, what you'll notice for group 4 is these are melting points, I think. Oh, boiling points. No, these are boiling points. And you start out at CH4 and you go down to SNH4, and you can see that the boiling point goes up. That's because the elements are getting bigger, more surface contact. And that's what you expect to see. So CH4 is really tiny, whereas SNH4 is really big. So the boiling point for the CH4 is going to be much, much lower than the boiling point for SNH4. And that's okay. That's what we expect to see. But look here what happens in these other groups. Now, if this trend was to be obeyed in these other groups, for the green one here, I would have expected NH3 to be down here, where I've got my arrow. Just because it's going to follow that line, right? So to be like minus maybe 120 or something. That's what NH3 should be. But look what it is. It's actually minus 33. It's actually about 100 degrees higher than it has any right to be. Look at HF. HF should be down here about minus 100. It's about 20. And look at water. Water should be minus 80, and it's 100 degrees Celsius. Crazy. But that's because the NH, FH, and OH bonds, hydrogen bonding, because those intermolecular forces are so strong, it pushes the boiling point to much higher than what we'd expect it to be. That's what this means. Okay, so that's the basic background of all of this. Does anybody have any questions at this point? Well, let me go through and show you some examples. I think that will help. And you'll see that really it's not as bad as all that. Okay, let's look at the Intermolecular Forces worksheet. There he is. All right. Okay. So these are examples of the kinds of problems that you'll see. The strategy I want you to use is to be able to figure out what the intermolecular force is at play in each case. Let me have this here. Let me move this around a little bit. Whoops. Okay, let's see what we can do here. I just don't have enough real estate in my screen. I need a bigger screen. Okay. So here's what we know. Here's what we know. We know. Okay. We know that van der Waals is going to be all CHs. We know that dipole-dipole is going to be CX. where X is non-metal. And
Is sorry, is van der Waal only CH or
Yep.
is it?
Yep. OH, NH, FH on the hydrogen bond. Okay.
Is there a fourth type of bonding?
I don't know, maybe. I'm only doing 3 here, Rebecca.
Okay.
There might be another one, I don't know.
I'm pretty sure there's also an ion dipole one, but I don't think
Oh.
we're really working with ionic compounds.
Nope, because we're in organic chemistry here. We're organic chemists, we're not whatever.
Inorganic chemists.
That's right. And we know as far as boiling point goes, H bond is going to be greater than dipole-dipole, is going to be greater than van der Waal. All right, so that's the summary. That's what I want you to be aware of. All right, let's take a look at this over here. Look at number 1. See that? What do you think that is? Do you think that's going to which intermolecular force do you think that is?
Van der Waal.
Why are you saying that?
Because all of the points are going to have carbons. So with those carbons, you have to have the hydrogens.
Right. So if you've just got straight lines here, that's all C's and H's. That's van der Waal. You know that from the outset, right? Yeah. Now look over here. What's the intermolecular force here with this one?
Hydrogen bonding.
Right. Yeah, it is. It's because you've got the OH. Now I know what some of you are saying. You're saying, well, hang on. You're saying that this has CH's in it, and it's also got CX's in it as well. Yes, it does. We're only interested in the highest force. That's the one that's going to make the difference. And because this one's got OH's, that makes it hydrogen bonding.
That's because the molecule is going to orient itself at that point and
Yep.
bond with others.
Yeah, that's right. That's right. So there you go. So what you would do is you put a VDW under this puppy, you put the H bond under the one with the OH, and that's the one that's going to have the higher boiling point. Any questions? No, I'm probably giving it away here, but it's okay. So looking at this one, these are both van der Waal, but this one's straight chain and this one's branched. See, it's got the branch off it. So the one with the lower boiling point will be the branchy one. There he is. Any questions? Now this one's interesting.
Can you repeat that? I'm
Sure,
sorry.
Sorry. The straight chain one here, he's straight chain. The other one is branched because it's got the line off it. And if you remember what I said earlier, the straight chain ones have more surface contact between them. So that means the boiling point will be higher. And this will be more like spheres in a box.
Okay, thank you.
Is that okay? Now look at number 3. Now he's a bit different. Now number 3, you might be wondering, is this branched? It ain't, right? Branching only applies to carbons off the chain. I'll say that again. Branching only applies to carbons off the chain, not these heteroatoms. This is actually straight chain. This one's actually straight chain as well. Right, so we're only talking about carbons. Right, that's the distinction I want you to make between these two. So straight chain and branch chain has nothing to do with number 3, but what does is the intermolecular forces. So this one, he's all CH. He's all CH, so that's going to be van der Waal. This one is CX, so that makes it dipole-dipole. The higher boiling point is going to be the dipole-dipole. Any questions? Okay, this one here, CX, dipole-dipole. This one here, OH, hydrogen bonding, lower boiling point, dipole-dipole. You're with me?
Yes.
Okay.
So this is how it's going to be like on the test. You're going to give
Yeah.
us like a series of them for one question.
Well, actually, I'm just going to give you one.
Or probably just one. Okay.
But yeah, that's it. But this is how it's going to be. I promise. Right? It's just going to be two things. You have to figure out which one is the higher boiling point, possibly the lower boiling point. All right. Now, the other thing we can talk about is solubility. So we all know that like dissolves like, and we can talk about hydrogen bonding solvents and van der Waals solvents. Now, a solvent is something that dissolves something else. We're only going to deal really with two kinds of solvents. And those would be the water as a solvent, and that's going to be hydrogen bonding because it's all OH. And then we've got, say, C6H14 or something like that. Could vary, but that one is going to be van der Waals. So what we notice is that things that have OHs in them tend to dissolve in water. Things that have CHs tend to dissolve in C6H14 hexane or van der Waals solvents. So I'll give you an example, water and sugar. Sugar's got OHs up the yin-yang. So sugar dissolves in water. What doesn't dissolve in water? Anybody have any ideas?
Oil.
Oil. What's oil? Oil is hydrocarbon. It don't dissolve in water, does it? No. But has anybody ever used a two-stroke engine? A two-stroke engine takes a mixture of oil and gasoline. Those things dissolve in each other because they're both hydrocarbon. Yeah, all right.
What about dipole stuff?
Oh, don't worry about them, Julie. That's sort of more in between and it's a bit ambiguous. So we're just going to stick to the extremes here. So if you were given these two compounds, you'd have to figure out what their intermolecular force was, as well as the intermolecular force of the solvent here, which is the H2O. All right, so the H2O is going to be hydrogen bonding. Which one of these two is going to have the greatest solubility in water? It's going to be this one that's hydrogen bonding as well. And that one there is van der Waals. So we're talking about compatibility here. Van der Waals, OH, hydrogen bonding, and hydrogen bonding. So the bottom line is water is hydrogen bonding. This one's hydrogen bonding. So they'll dissolve in each other. Any questions? Lesser solubility in C6H14. So this is van der Waals. C6H14 is van der Waals as well. And the one with the lowest compatibility there would be the hydrogen bonding. So again, that would be the answer. Anybody got any questions? All right, what about this one here? We've got van der Waals, we've got dipole dipole. The lesser solubility in C6H14 would be the dipole dipole. The van der Waals would be the most. But this is lesser solubility. I'll stop there for a second. Does anybody have any questions?
Okay, so do you know when it's lesser solubility with the hydrogen bond? Is that what you're saying?
Well, what I'm saying is that it's compatibility. If we know C6H14 is van der Waals, then the most soluble thing in that will be van der Waals. The least soluble thing will be the dipole dipole out of these two.
Okay, so it just goes based off of the weaker or the weaker ion force.
No, it really goes by compatibility. What I'm saying is what's compatible, like dissolves like. Van der Waals is most compatible with van der Waals. But if you're looking for lesser solubility, it'd be the one that isn't van der Waals.
And is that always, or is that just like in this case?
No, it's always.
Okay.
Okay, but look at 9 and 10. These are a little bit different. These are a little bit harder. you'll notice we're looking for greater solubility, again, in a van der Waals solvent. But this one here is dipole-dipole, and this one here is hydrogen bonding.
Mhm.
But if you look at what I had said earlier about this is the hierarchy here. So it turns out that in this case, the one that has the greatest solubility in C6H14 will be the dipole-dipole, because it's out of these two, it's the more compatible with van der Waals. Hydrogen bonding is least compatible with van der Waals. So think about this as being like oil and water, the van der Waals and the hydrogen bonding.
Okay, and then you said dipole dipole is more compatible with the van der Waals, right?
That's right.
Okay, thank you.
You okay with that?
Yes.
All right. Does anybody have any questions?
So their compatibilities are basically opposites. If you just take it and flip it, it's the other way around for the hydrogen bonding, correct?
Yes, that's exactly right.
Okay.
Yeah. So for this one here, in solubility in water, the one that's more compatible with the hydrogen bond is the dipole-dipole again, and not the van der Waals. So again, oil and water. Think of it that way. All right. So what we'll do, let's see, what time is it? Very close to quitting time here. I am going to very, 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 very quickly, since we've just got about a minute. Actually, we don't have a minute, do we? We lost a minute. No, we'll leave it there. All right, we're running out of time, but we'll continue on Monday. Okay. Does anybody have any final questions here? Actually, I'll tell you what. I'm going to hang around. If anybody has any questions, you can ask me, but I'll let everybody else go.
Thank you. Have a great one.
Okay, thank you. See you all later. If anybody wants to hang around, they can.
Thank you.
See you in lab.
Yes. See you in lab.
I have a question about nonpolar covalent. I wanted to ask it later. Can I?
You can ask now.
So it's the same elements, but does it matter if it's the same non-metal, or can it be metal, if the difference, delta difference end up being zero?
No, just non-metal.
Just non-metal.
Yeah, because you're talking about alloys, then Victoria, that's a different kettle.
Oh, okay.
Yeah, that's mixtures of metals. We're not dealing with anything like that.
Okay.
That's a metal bond is a completely different kettle of fish.
Let's not go there.
Let's not go there. I agree. Natalie, Nora, you guys okay?
Yes, I had it wasn't really a question. It was more about the email you sent about the accommodations.
Yes.
I do.
Do you want to talk privately about this, Natalie?
No, you're fine. It's just quick. I don't have any classes after your classes, so I'm perfectly fine to take it at normal time with everyone else.
Okay, I'll just extend your time.
Okay, cool. I just wanted to let you know I didn't feel like having to reply, and you know.
All right, sounds great.
Okay, have a good weekend.
Cheers, Natalie. Bye. Morgan, you all right? Nope, she's gone.
I'll see you in the lab as well.
All right, Victoria. Bye-bye.
All right, bye-bye.